In this part of the episode, that is episode 4b, I am going to describe that the assumptions that we normally make, that is uniform volumetric rate of heat generation in the fuel pin of a nuclear thermal power reactor for the ease of calculations, is conservative with respect to central line temperature of the fuel pin. So let us get started with the proof. Before that, I want to give an introduction to those people who are not in the field. The heat is generated in a nuclear water reactor generally and mostly in cylindrical fuel pins which are placed in the reactor core due to nuclear fissions. But the temperature of these pins is to be kept below a limit so that their physical geometry does not get affected. The temperature rises because heat is produced in these fuel pins throughout the volume of the fuel pins. And this heat generation is known as volumetric rate of heat generation. Normally, it varies with the radius of the fuel pin. The magnitude of this volumetric rate of heat generation varies with the radius of the fuel pin and with time. So, the radial distribution of this volumetric rate of heat generation, which from now on I will call in short form as VROHG, is more or less axisymmetric. That means at a fixed distance from the axis all around, it will be same in a fuel pin. But the estimation of this heat generation is very complex and is dependent on the type of water reactors. But before we go into what assumption we make for ease of solution, let me describe what is VROHG. We need to know in detail what is this VROHG at a point in the fuel pin. It is the amount of heat generated in a small volume per unit volume around the point in a small time per unit time, as both volume and time tend to become very small because this VROHG changes with radius, with the space and time. But normally, as I said earlier, it is axisymmetric and it does not vary in circumferential direction, and the gradient is very small in axial direction, which can be neglected with respect to its amount of heat flow in radial direction. So if V is the volume and T is the time over which you have estimated a total amount of heat as Q, then VROHG is nothing but Q divided by volume and divided by time. If you look at the figure A, it represents schematically a fuel pin of a nuclear water reactor. The fuel pin is cylindrical in shape and consists of uranium dioxide pellets. If you see the figure B, it represents what is the volumetric rate of heat generation in a thermal reactor. What you see that the heat generation is highest at the surface of the pin and lowest at the center of the pin. The trend is that it decreases as you move towards the center of the pin. While if you consider the same case for a fast reactor, opposite is the case. You will find the heat generation increases from surface as you walk towards the center of the pin. But if you look at the temperature in both the cases, the temperature always rises from the surface towards the center. This is because we assume that the heat flows only radially outwards. Circumferential temperature gradients, that is the variation in temperature, is zero, and actual temperature gradients are so low that they can be neglected as compared to the radial temperature gradient. That means the heat flow in axial direction can be neglected as compared to the heat flow in the radial direction. This figure represents the cylindrical cross section of a fuel pin, and you will see that the heat flow is only in radial direction. So let us assume a cylindrical surface inside the fuel pin. This is an hypothetical surface. We want to see what is the heat flow across the surface of this hypothetical cylinder. You will see that the total heat flux flowing out of the surface of the reactor in the two cases. The first case is where we have assumed the uniform volumetric rate of heat generation, and the second case is what is the actual volumetric rate of heat generation. You will find that in case of a thermal reactor, both the amount of heat flowing out of the surface start from zero and they end at the same point, because the total heat which is generated in the fuel in both the cases is same. But the uniform volumetric rate of heat generation is higher in the beginning and becomes less towards the end, while the actual volumetric rate of generation is smaller than the uniform case in the beginning, that is towards the center of the fuel pin, but it rises sharply and meets the other case at the surface of the fuel pin. Before I proceed further, let me talk a little bit about the assumption we are making. We are making the assumption that heat generation, that volumetric rate of heat generation, does not vary along with the radius. It is uniform throughout the volume. That is, if the amount of heat, total heat generated per unit time in the fuel pin is Q, and if its volume is V, then V ROHG will be equal to Q by V per unit time. And we make this assumption to make our calculations easy. For design purposes, the Nuclear Power Plant Safety Code requires that the central line temperature to be below the safety limit and to be conservatively estimated. For example, in this case, conservative means it should be higher than the actual temperature which is likely to occur. In the absence of knowing completely the radial VROHG distribution, because it is very difficult to estimate accurately, but its shape and peak value can be estimated conservatively with a lot of confidence. A conservative assumption is to be made so that we can do this calculation easily, as total power generated in the pin can be accurately estimated and controlled, because this is derived from the temperature difference of the coolant. So we can assume a uniform VAR-OHG it is higher than the actual distribution at center of the pin and lower than the actual at the surface of the pin. For thermal power reactors, it is different for fast power reactors. But we must see that the total power which is generated in the pin, either by assuming uniform power distribution or actual power distribution, in both cases it should be same. The designer only has to prove that the assumption which he has made is conservative. In this figure, we will see how this assumption of uniform volumetric rate of heat generation looks like as compared to the actual volumetric rate of heat generation. So we see, as we move along the radius, at the center, near about the center, the uniform VROHG is much greater than the actual VROHG. So naturally, the heat flow from the surface of a assumed cylinder R will be much more in case of uniform heat generation. But as we move along, the actual VROHG becomes higher than the uniform VROHG. But this does not mean that the total amount of heat flow across the surface of a cylinder in this region of radius R will be greater in case of actual case, because the total amount of heat flowing outside at the surface of the cylinder, at the surface of the fuel pin, becomes equal in both the cases only at the surface of the fuel pin. And so we say, though the actual VROHG is higher in part of this radius, but the total amount of heat flow across the surface is always greater in case of uniform case. It is seen that in the case of assumed uniform VROHG for a thermal reactor, the total heat flowing out is always greater than the actual case, except at the center, where in both the cases they are equal. Consequently, the temperature gradients will be higher along the radius for a thermal reactor. As surface temperature of pin is same in both the cases and is controlled by the coolant, the central line temperature will be greater for the uniform case because of higher gradients, thus proving that the assumption is conservative. This proof is not available in the current popular textbooks. For fast reactors where VROHG is lower than the actual in the center and higher than the actual at the surface, the same assumption may be made by many without being aware that it is not conservative in that case. Thank you.